All right, so my name is Lynn Root. Welcome to my talk. I am an SRE at Spotify. A funny little story. You might have noticed that my last name is Root, and it's real. I didn't change it. And when I first joined Spotify 3.5 years ago, I actually requested Root as my LDAP username. But they wouldn't let me have it, so that was too bad. Okay, so there are a lot of cool, interesting technologies, right, for the SRE world. We have Docker and Kubernetes and some lightweight operating systems and maybe even some chaotic monkeys running around. So it's a really awesome, fun time to be alive, right? But not for me. I actually like the boring. I like the tried and true. And at Spotify, we have a history of loving boring technologies. So it's not that often that people talk about DNS. And when they do, it's usually to complain. It's always DNS. And or when there's a major outage. Otherwise, the DNS is initially set up, probably by a third-party provider, and then mostly forgotten about. But it's because DNS is so boring that we love it so much. It provides us with a stable and widely known query interface, some free caching, and service discovery. And actually, earlier today, I was talking with one of my colleagues. He asked, do we actually love DNS? And I mean, of course we do. We kind of have to. It's kind of like you have to love your younger brother. You don't have to like them. But how else are we going to get all those awesome cat gifs? I don't know. All right, so that landed well. In this talk, I'll walk through how we've designed and currently manage our own DNS infrastructure, curious ways in which we use DNS, what we've learned when we push DNS to its limits, and what the future holds for DNS at Spotify. So jumping right in, we actually host our own DNS infrastructure, which I guess is pretty unusual lately. But it's a pretty typical setup. We have what's called a stealth primary and a hot standby running bind. And it only has one job, which is to compile zone files. We then have a bunch of authoritative name servers, or secondaries, which also run bind, with at least 2 per geographical location. And when the stealth primary is finished recompiling the zones, a transfer happens to those name servers. And as a side note, 4 of those name servers are actually exposed to the public. So then we have a bunch more resolvers, with at least 2 resolvers per data suite location, all of which run Unbound, which is a recursive and caching DNS server. And our resolvers are actually configured to talk to every one of our authoritative name servers for redundancy. And under normal conditions, Unbound randomly selects a name server to send queries to based on a round-trip time band of 400 milliseconds, which is kind of slow. So that unfortunately means Unbound will not always select the fastest responding server, but with our geographical setup, it usually does. And so also on every deployed service host, we have Unbound running locally, directed to use our DNS resolvers within the services region. We use Unbound everywhere because it gives us caching that we'd rather not implement ourselves. And we also have always relied on DNS for service discovery, so Unbound helps us to avoid many requests from individual services that could effectively DDoS ourselves. In addition to running Unbound on every service host, we have the services that are built using our open source microservice framework called Apollo. It also has DNS Java, which provides us with yet another layer of resiliency. The DNS Java library will actually cache records for an hour if the local Unbound service fails or if our resolvers are failing. And so, like many tech companies, we have grown into better practices. We did not always have this setup of automatic DNS record generation and deployments that did not require any babysitting. Before the push to automating DNS deploys and zone data generation, we hand-edited our zone files and committed them into version control, and then manually deployed them with a script that we ran on our primary. And then to forewarn others of the possible service issues, our script included a little shout out to the SRE channel that DNS DEPLOY was upcoming. However, after feeling too much pain with manual edits and deployments, in 2013 we made an initial push for the automation that we have now. We started first with making incremental pushes to script our record generation. Then we added the requirements of peer reviews and integration testing for records that still needed manual edits, like those marketing-friendly CNAMEs. And then finally, in 2014, we were comfortable enough to sort of forget about DNS after setting up cron jobs everywhere for regular record generation and DNS deploys. So in detail, these are my little cron images, I guess. We have a pair of cron scripts written in Python that are scheduled to run every 10 minutes that are staggered from each other. One script generates records for our physical fleet by talking to what we have called ServerDB, which has all the information about our physical servers. And then another script talks to a Google Compute API to get all of our cloud instances with deployed services in Google Cloud. And that scripts take about 4 minutes to get a list of instances for every service, and then finally commit into our DNS data repository, of which we consider our source of truth. Then we have another cron job, which will run about 3 minutes after the initial git push. The stealth primary hosts this cron job, which runs about every 5 minutes. And that simply pulls the DNS data repository and then compiles all the zone data. And so with every compile time, we actually, which takes about 4 minutes, we update a particular TXT record that reflects the git commit hash of what's being currently deployed to production. And then once that's done, the primary notifies all of the authoritative name servers of potential changes. And then the name servers then query the primary to see if there are any changes. And then if so, it initiates an authoritative transfer or an AXFR. And these transfers to the name servers also take about 4 minutes. So for any of those who are too uncaffeinated to notice or too far back to see, it takes at best 15 minutes for a new record for a new host to propagate in our DNS. Maybe you're thinking, what about service discovery? Maybe. Our SRV records also used to be handcrafted. This was, of course, problematic. Typically, changes to DNS are relatively slow, as you just saw. But service discovery needs to move fast. And then couple that with manual edits being prone to human error, we needed a better solution. So earlier in the infrastructure overview, we have services running unbound locally, talking to our resolvers. And then in a typical Spotify fashion, we built our own service discovery system, which we refer to as Nameless, supporting both SRV and A records. And Nameless essentially allows engineers to dynamically register and discover services, which of course makes it easier to respond to scaling needs. On to monitoring. Historically, DNS is quite stable, but nevertheless, shit happens. There are a few ways that we monitor our DNS infrastructure. We collect metrics emitted by Unbound on our resolvers, including the number of queries by record type, serve fails, and net packets. We also monitor our record generation jobs for gaps or large differences in total records generated. And then most recently, we built a tool that allows us to track response latency and availability and correctness for particular important records and deployment latency. And for the internal measurements, we just use DNS Python to query our resolvers and name servers from their respective regions. But then for the external, we use Pingdom's API, where we grab and record the response latency for our public name servers. And while Pingdom's monitoring is extremely valuable for us, we found it quite difficult to tease out from where they send their queries to measure latency. As you can see in this graph, it's quite volatile. Currently, we have global server load balancing, GSLB, with both Dyn and NS1. and this allows us to send requests of our most popular services to the closest cluster, providing users with the best latency. However, we had not always had this dual provider GSLB setup. Among many others, we were affected by the DDoS attack on Dyn back in October last year. And not only were our users affected, but employees were too. Our monitoring did not work, our VPN was down, internal login no longer worked as well, and then PagerDuty was also affected, so we had very limited ability to easily page others. And not only that, we were in a bit of a pickle because we could no longer access our private Git hosting, the centerpiece of our infrastructure. And then the cherry on top was we needed to go off of the not touched in 3 years documentation for all the manual DNS deployments. So while essentially flying blind, we moved ourselves entirely off of Dyn. For internal services like employee login and VPN and Git hosting, we just pointed records directly to the hosts. For our web presence and for connections coming in from any of the Spotify clients, we just moved our access points to Amazon's Route 53 for no other reason other than an SRE already having an account set up with AWS. Once we were comfortable with that Dyn service had stabilized, we moved back to our original setup, but then we also added NS1 as another provider for redundancy. And NS1 was chosen over Route 53 for a couple of reasons. Unlike Amazon, NS1 allows us to limit the amount of records returned to avoid TCP fallback, which some of our older Spotify clients can't really handle that well. NS1 also supports a more refined geolocation routing compared to Route 53's Anycast setup. All right, so beyond its typical uses, we leverage DNS in what I find interesting ways. So there will always be clients that cannot connect to Spotify at all. In order to track the errors and the number of users affected and to circumvent any potential restrictive firewalls, we introduced error reporting via DNS. And so the setup is when there are issues, the client would make a single DNS query to a very specific subdomain that mapped to an error, and it had all of its relevant information in the query itself. And so the queried DNS server will then log it, and those logs are parsed and tracked into this lovely Kibana graph, which I conspicuously left off the y-axis. Another use, we use DNS as a DHT ring, with TXT records stored as some service configuration data. One implementation for this is for song lookup when it isn't already locally cached on the user's client. So when a Spotify client looks up a requested song, the ID itself is hashed, which is a key along the DHT ring. The value is then associated with the key, and it's essentially the host location where the song can be found. So in this very simplified case, instance E owns from 9E to C1, and then instance E points to a record, something like tracks.123.storage, whatever. But that's not actually the real host. It actually just directs the client to query the LUN6 storage hosts via port 1234 to find that song. We also created some records to help engineers quickly see all of the machines associated with a particular microservice. At Spotify, every machine is typically has a single role assigned to it, which is a Spotify term for a microservice. So by using the role that you are interested in, you can dig the roles zone to get a list of host IPs. And then you can use pointer records to get their fully qualified domain names, which is just a little handy tool that we use. Only when you entangle yourself in DNS do you realize new ways to break it, some weird intricacies and some esoteric problems. And there is certainly no better way to bring down your entire service than to mess with DNS. So a few years ago, we migrated our entire fleet from Debian Squeeze to Ubuntu Trusty, including the gradual migration of our authoritative name servers. We rolled out one at a time, testing each one before moving on to the next to ensure that it could resolve records and for the public name servers to receive requests on ETH1. Upon migration of the final name server, you guessed it, DNS died everywhere. We were offline for about an hour, and the culprit turned out to be the difference between firewall configuration between the two OSs. The default for Trusty did not allow for port 53 to be open on the public interface. This was essentially missed because only DNS top was used to test connections received, but the public interface wasn't directly queried, therefore missing rejected requests. We also realized that scaling can be difficult. So in support of our data infrastructure, we have nearly 2,500 hosts dedicated for Hadoop secondary roles. And each host has an A record and a pointer record. However, pointer records are typically longer than A records, and when queried, we only got back about 1,800 hosts, which then of course makes sense because the message size of the complete response was larger than the TCP packet size limit. But what was a bit of a head scratcher was when our resolvers just returned nothing for the same pointer query. Only our auth name servers were responding to them. And after a few days of digging into bind and unbound with plenty of TCP dumps, we couldn't really figure it out. However, just like the other day when I was researching for this, I found a tiny little blurb in the unbound documentation that says it'll drop any response that is larger than a packet size. So that was a peculiar head scratcher for us. And so at Spotify, we also been using Docker to ship code faster and with greater confidence, but it hasn't always been smooth sailing. Some of our services use host mode networking, where the container has the exact same host network as the stack of the host, or the network stack of the host. So when upgrading from Docker from 1.6 to 1.12, we noticed that requests to the host unbound were being rejected. This was because when using 1.6, the source IP appears as localhost. However, on Docker 1.12, the source IP appears as the ETH0 IP of the host, and therefore is rejected by our unbound setup. And so despite this upgrade being gradually rolled out to the services using containers, it affected over half our current active users for over an hour, which is fun. So for the most part, our DNS infrastructure has been pretty stable. It doesn't require a lot of babysitting, but it's certainly a lot of pressure, especially if we mess something up. It has the potential to impact a lot of users, as I just mentioned before. So at Spotify, we've been focusing a lot of effort around the concept of ephemerality. We want our engineers to not treat hosts as pets, but as cattle. But our infrastructure sort of prevents this concept. As you might have remembered, our propagation time for new DNS records is agonizingly slow, at best 15 minutes. But on average, new records are propagated and resolvable within 20 to 30 minutes. And this is far from ideal when you want to scale quickly, and much less so when you're trying to respond to incidents that require changing a service's capacity. This issue had largely gone unnoticed because it takes fairly long time for our physical servers to boot up and install required services and packages. But yet, when we were moving to the Google Compute instances, they are up and running within minutes, sometimes faster, which in essence exposed the record propagation latency. So as a recent hack project, a colleague and I played around with Google's Cloud DNS offering. We plugged into Cloud DNS's API into our capacity management workflow, where as soon as a request was made for an increase in capacity, our hack would be to just add the IP and the host name directly to the Google managed test zone. And the results were pretty damn remarkable. New records were propagated and resolvable in less than a minute after the initial instance request, essentially improving propagation time by an order of magnitude. And I think our demo actually went so fast that not many people actually caught the improvement or the purpose of the hack. I think it just went by too quickly for them. So eventually we will be handing off our DNS infrastructure to the folks that probably know how to handle it better than we do. And hopefully we'll be able to turn off PagerDuty for DNS. So recap, I kind of blew through this presentation a little bit quickly. I started off with an overview of our infrastructure, how slow our record generation and deployment is, and how we are still plagued with the not invented here syndrome by building our own service discovery, and also went through how we monitor DNS and how we've set up our global server load balancing. I also talked about how we use DNS beyond what it's typically known for, making use of its distributed architecture and caching. And then humbly walk through some lessons learned as we have been running our own DNS infrastructure. We exposed some interesting issues. And then finally, I just gave a peek about what the future holds for the boring technology here at Spotify. All right, thank you. All right, I know I have like 5 minutes for Q&A, but I get like super nervous when I'm put on the spot. So if you have questions for me, I'll just be like right outside, and maybe my colleagues can join me and help answer questions. But thank you.